Good afternoon and welcome to Carl and Cymru revision sessions. This session will focus on Equilibria and will be presented by Ms Stevens from Bropedo School. The session will last around 45 minutes where the teacher will go through the relevant subject content. If you have any questions, please use the question and answer section and I'll endeavour to answer your questions during the session. The session will be recorded with the recording and any relevant resources uploaded to the e-sgol website in the Carl and Cymru area.
Good afternoon to all of you. It should be worth noting before some of you sit through unnecessary sessions that this is exclusively for the triple award content, which is Equilibria. If you study double award, there is ample resources available to you on the Camera Cymru site though, so please feel free to dip into another session. But this is a subject that is the last topic for the triple award separate chemistry course. Okay, so as it says there, reversible reactions is what I will be covering this evening. Now, it is something that is relatively new to most of you because up until this point, I'm sure you've understood the fact that most reactions go forward from reagents to products, and that is the end of the matter. Well, the reality is that is not in fact the truth. Well, not the whole truth anyway, okay? There is a small class of reaction where this isn't strictly true and the products can in fact reverse and recreate the original reagents. Okay, so that is what is meant by the reversible reactions. Now, some of you might already be up to speed with quite a lot of this. Some of you might not even have got as far as the final unit yet. So what do you know already? Well, I'm sure that will vary from person to person. Okay, so I'm going to go through some basics and then lead into the two specific examples that you will need to know for the triple award course for the WJC. So reversible reaction, as it says there, it is a reaction that occurs in both the forward and reverse direction. It's new, it's a bit odd to get your head around it initially, but go with it, okay? So it's a reaction that goes in both directions. Now, in most circumstances, we write, as I'm sure you see, if we've got two reagents, let's say A and B, okay, we tend to write it that might make C or D or both, okay? This is the crucial thing that I need to get clear for you this evening, is that actually for this class of reaction, we won't be or should not be using this symbol, okay? So if I just, sorry, get rid of the error, well, not error them, but the incorrect one for you, so that it's clear what I'm talking about. The reversible reaction has this new symbol for some of you, which is a double-ended arrow in certain circumstances, but it's not double-ended arrow as you can find in some packages such as Word. Okay, it is a half arrow in one direction and a half arrow in the opposite directions. Okay, do not be tempted to put in this symbol. Okay, they do not like it. Okay, so to be clear about what I'm saying here, okay, let's say we have A and B as reagents and they traditionally would form C and D as products. What I'm telling you is that A and B do still indeed produce C and D as the products, but at the same time, C and D can react with each other to reproduce or reverse themselves into A and B. Okay, now I'm hoping that most of you have been tuning into all the sessions that we've had over the last month. If you have, or if you watch them from the Carl and Cymru site, then what I'd like to draw your attention to is just draw you quickly back to the second session I did, so 2 weeks ago this evening. Okay, so what I said in that session too, and I hopefully made clear to you, is that energy can't be created nor destroyed. Okay, so the amount of energy released in one direction is exactly the same as the energy absorbed in the opposite direction. So to put it into the context that we had that evening 2 weeks ago, the energy to break a bond is an endothermic process, so it requires the input of energy to break it apart. But let's say breaking a bond between two hydrogen atoms would require 200 joules. Okay, the reality is that if you then take those two hydrogen atoms and recreate the molecule H2, so you're making it, that would then liberate or release the exact same amount. So breaking a bond and making a bond is the same amount of energy. In this sense, if a reaction can go forward in one direction, releasing or absorbing a certain amount of energy, going in the reverse would do exactly that. It would reverse the same amount of energy. So if it gives out 200 joules of energy, If the reaction goes in reverse, it would take in 200 joules of energy. Okay, so A and B, making C and D, let's stick to this generic model initially. Well, I'm telling you that if the reaction releases energy in one direction, so that is, if you remember back to the proper word there, we say exothermic. Okay, so it gives out excess energy in the forward reaction. The reality is then that it will absorb exactly the same amount in the opposite direction. So by that, I mean, if you're going to reverse the process, that would be described as an endothermic reaction. So going forward, releases energy, going reverse, absorbs it or takes it in. Okay, so it's important that you get your head around this, because when we get to the conditions and the chosen conditions for certain reactions to be performed under, this will be crucial. Okay, so if we look at a simple example initially, now it's something that you've all seen since probably year 7 upwards, is the blue chemical copper sulfate. Well, what you might not know is that copper sulfate, okay, the colour it is, which is that distinct blue, because it is what we call hydrated. So it's got water molecules present in it. Now, if you then heat it up, well, obviously, I'm hoping you can all grasp this fact. If it's heating up, I'm describing what here is an endothermic process. What you will see is that it will give off the water vapour, so it stops being hydrated, and it will turn the blue solid into a white one, which is called anhydrous. So we've got rid of the water molecules. Okay, so if this process was therefore an endothermic process, because I had to input energy to make it happen, the reality is if I then take the next one and I go backwards by adding a few drops, this must therefore be an exo. Apologies. Okay, so by adding water to anhydrous copper sulfate, you're actually going to release some energy. Okay, and that is because getting rid of the water molecules in the first place required the input of energy. So the equation for what's happening there, this is what I mean by the hydrated, the classic blue that you have there. Okay, so copper sulfate is often surrounded by 5 molecules of water. If you heat it up, it becomes anhydrous, so the white version of CuSO4, and it gives off some water molecules. Okay, so hydrated copper sulfate becomes what we call anhydrous copper sulfate, and it evolves or gives off water. Okay, now in that sense, if you turn it into the symbol equation I showed earlier, what you have is CuSO4 and the water molecules then being given off freely, but as always, is central to chemistry, as you've learned by now, hopefully. You have to balance that, so you'd have to have 5 water molecules being given off, okay? So let's be clear, what in this is the exothermic reaction? Well, in order to go forward, I had to supply it with energy, okay? So this must be, therefore, the endothermic process. So that was what was endothermic. And in that sense, going reverse then must be the exothermic reaction. Okay, so be clear, one direction will always be the opposite of the other. So exothermic in one direction will automatically mean if it reverses, it becomes an endothermic process and vice versa. Now, it's important you get your head around this in a closed system point of view as well. Okay, so if you think about it as being sealed, so nothing can escape and nothing extra can be put in. Okay, so imagine a closed system where no reactions are added and no products are removed either. Okay, just to get your head around what I'm trying to get you to understand. What I then mean that is if you've got A and B going to C and D, keep it as simple as we can as a model initially. A and B will continuously be combining to form C and D. But at the same time, C and D are combining with each other to reform A and B. So it's sealed, nothing is leaving, nothing is entering the system. So it's a closed system. And at the same time, you've always got these 2 reactions happening. It's going forward, but at the same time, it's going in reverse. Now, eventually what will happen if you leave it in this closed system and don't do anything to interfere with it, is that you will reach a point where those 2 reactions are occurring at the same rate. Now, just to recap, rate was something you covered in year 10. It was one of the final units. I think it was unit 5 in year 10. When I talk about rates, it simply means how fast it's happening. So eventually what will happen is that A and B will form C and D at a certain speed, but at the same time, C and D will form A and B at the same speed. So what you'll notice is nothing, okay, because there will be no overall change. That is described as a system that is in dynamic equilibrium. So it's a reaction that goes forwards at the same time as going in reverse at exactly the same time. So there's no overall change. You will have a constant amount of A and B, and you'll have a constant amount of C and D, because just as soon as A and B are making C and D are remaking A and B. Okay, now what is important here then is getting your head around the temperature and its effect on equilibrium. So if, as I said already, if the forward reaction going from left to right then, so when I say, and I will use this a lot for the end of the session, okay, so if you're talking about the forward reaction, I'm talking about what is classically described as being the reactants on this side and the prods being on this side. So I'm talking about going in that kind of usual direction that you are familiar with. So the forward reaction is going from left to right is endothermic, then heat is taken in. Okay, you have to supply energy to get that reaction to proceed. Okay, so if that temperature is increased, what you're actually doing then is supplying it with even more energy. Now that's a positive thing, that's a good thing, because it requires energy to make it proceed or go forward. So what that means is that if you increase the temperature, you are going to eventually increase the yield of products, okay? Because if going forward requires heat and you're supplying it with the heat, then it'll go forward a bit more, okay? Now, that is only true for endothermic reactions, though. In the same sense, though, if you decrease the temperature, it's not going to like it, because what it needs is an input of energy to make it proceed in the forward direction. So if you decrease the temperature of an endothermic reaction, it will therefore be unable to proceed as much as it used to. So the yield is therefore decreased because it's taking in less heat because there's less heat being supplied to the system. So endothermic, you really do want what they say is a high temperature, because high temperature means that you're feeding that reaction and it will proceed a bit more, and the yield, so how much you get out to the reaction, is a slightly better one. Okay, as is the case often in chemistry, you take the opposite principle and the results are exactly that, the opposite as well. So if you think about a reaction that's exothermic, be clear here, a reaction is exothermic if it has an excess amount of energy. It's got too much. It's got so much energy, it's giving it out to the environment. What it certainly will not appreciate, therefore, is you giving it even more energy. Okay, so if a reaction in the forward direction is exothermic, then it is giving its excess or spare heat energy out to the environment or the surroundings. Okay. The effect, therefore, of increasing the temperature is detrimental because it's already got too much. So you give it even more and it will go in the direction that is capable of absorbing it, which in this case is that direction. Because if you remember what I said earlier, if it's exothermic in one direction, apologies, just let me quickly get rid of that. Just got a mind of its own this evening. If going that way is exo, so just to remind you, going in reverse is therefore going to be endo, okay, which therefore requires heat. If you've got an exothermic process and you're supplying it with a high temperature, the only way it's going to be able to use up that energy you're supplying is by going in reverse, going backwards, okay? So that results in the yield of the products being decreased because less heat is being given out, okay? So if you then decrease the temperature, then obviously that's going to favour the forward reaction because it's a way of it, therefore, not having to get rid of as much excess energy. So if you decrease the temperature within an exothermic system, the yield is slightly increased. Okay. Now, what we will look at, therefore, is on first sight, you might think, right, great, exothermic, I'm always going to use a low temperature. Endothermic, I'm always going to use a high temperature. If life was that simple, it'd be great, wouldn't it? But there is always, as is the case in chemistry, often enough, there is other factors you must consider in order to get what they call an ideal or optimum conditions, okay, but we will come on to that in a minute. Right, so what are our gases? Some of the reactions, and certainly the ones that you need to know in depth for the final unit, which is the Haber process and contact process, involve gaseous atoms. Okay, so what about gases and equilibria? Does that have any further considerations you need to think about? Well, yes, it does. Okay, so pressure and equilibria, as I'm sure you're already aware of. Okay, if you've got a highly pressurized system and you decrease that volume, you are increasing the internal pressure. Okay, so increasing the pressure will push the reaction in the direction of fewer molecules in that case. Because if you look at it, what I've got here, okay, I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got a magic number of 8 molecules of reactant, but I've only got 4 molecules of product. Okay, what that means is even though I've got exactly the same amount of atoms, because the reality is atoms can't be created nor destroyed. One of the fundamental kind of facts you learned very early on in year 10, I hope, is that there's an interesting fact about gases, which is it doesn't matter what the gas's composition is. So it doesn't matter how many atoms are within that mole or molecule of that gas, it will still occupy the same volume. Okay, so if you have a reaction that has a decrease in the number of molecules from beginning to end, so reagents to products, what that does is by going forward, it naturally decreases the internal pressure of the vessel, okay, which is the case in this argument here. Okay, so increasing the pressure will push the reaction the direction of the fewer molecules, and as we established, it was 8 this side going to 4 this side, which means if you increase the pressure, it'll go, do you know what? I need to decrease the pressure naturally myself. Let's just go madly in the forward direction. Okay, so considering pressure is slightly more straightforward than the temperature one, you literally do need to look at which side has the smallest number of molecules. Okay, and then you need to consider if it's shrinking in number of molecules, it will favour high pressure. And if it is increasing the number of molecules, then actually it needs to be performed at the lowest pressure possible. Okay, so pressure and equilibria can be a bit more simplified in your thinking, in the sense, look for the side with the smallest number, and that's the side that will be favoured or be pushed towards by having a high pressure. Okay, right. So this is where we need to look at specific examples. Now, there are 2 specific examples for year 11 content. So the first one is called the Haber process. Okay, now the Haber process sounds all glamorous, admittedly, okay, but it is simply a version of making this compound here, which is called ammonia. Okay, not pneumonia. Quite comical, except when you're an examiner like I am, it can be a bit disheartening to see so many people mistakenly call it pneumonia. So ammonia is the compound that gives urine that quite distinct aroma, should we say. So it's got a potent smell as ammonia. It's present in urine. Specifically, you can smell it being similar to possibly cat urine. Okay, so ammonia has the formula NH3. Now, NH3, as I'm hoping you can therefore work out, is made from nitrogen atoms and hydrogen atoms. Okay, now both of them are diatomic gases. Okay, so think back to year 10 and you revisit it in year 11. Diatomic means that they will go around in pairs. So as you can see, okay, we've got hydrogen as a dimer. Hydrogen as a dimer there, you've got nitrogen and you've got hydrogen, okay? Keep in mind the fact that I said that every gas has the same volume, okay? So it has this same spatial occupation. Doesn't matter if it's hydrogen or nitrogen, or in this case, the product, which is ammonia, which will be gaseous as it's being produced, okay? So basically means think of it as blocks, I suppose. So this side of the system would have 4 moles of gases to occupy that space. And by going forward in this direction, okay, you then have half as many molecules of gas, and therefore the pressure will suddenly halve just by going forward. So you're going from 4 molecules to 2, so you're shrinking the pressure. We'll come back to that in a few slides' time when we consider the conditions. Okay, so if I get you to focus on the formulas then, I said that you had ammonia being made from nitrogen and hydrogen. It's important and part of the syllabus that you also therefore know where we get them from. Okay, so where do we get the nitrogen and the hydrogen from? Well, nitrogen, I'm hoping you can recall from year 10, is 78% of the air around you. So it's not really any shock that we can get the nitrogen out of the air itself. Now, we can't just get a bit of air and say, oh, do you know what, let's just shuffle it up and let's just grab a bit of nitrogen out of it. Obviously, you're going to have to process it. And it's a similar process to what, if you've looked at lots of the Cummery sessions, it's the one where we were discussing crude oil. Now that's separated in exactly the same fashion, which is by fractional distillation. So you take it and you get them to evaporate and condense at different temperatures based on the fact that they've got different boiling points. So nitrogen, its source is the air, and it is recovered from the air by fractional distillation. So that is a fact you need to know where we get it from. The other one is slightly more complex, okay? So we can get it from natural gas. It's not as straightforward, and by now industry is leaning towards the preferential method of getting hydrogen out of the electrolysis of water. So again, you'd have studied that in the metals unit when you did electrolysis. So that's unit 3 in year 11. What you learned is that you can take water and split it up into its constituent elements, which is hydrogen and oxygen. And that is therefore potentially used to create this hydrogen that you can then feed into the Haber process. So why study the Haber process? It must have some significance. Why is it so important? Well, the reality is plants, crops, okay? Now, I don't often big up biology. Me and biology don't always get along, but I'm hoping that through your year 10 biology, you're already quite familiar with the workings of plants and the fact that they require nitrates in order to be healthy and to grow. Okay, it's part of the process by which they photosynthesize and stuff as well. So you're already aware that nitrogen as an element is superbly important for plants. Okay, not quite so important for animals, but for plants, the nitrogen is important. Now, it'd be great if plants could access it directly from the air, but they can't. Okay, so plants need this nitrogen to grow. And the fact that they can't access it directly from the air, despite 78% of what is around them is what they want or need immensely, they can't access it through the air directly, so they have to access it from nitrates present in the soil. So they absorb it through their root systems. All this, I'm not going to go on too much about it because this is covered in quite a lot of detail in biology. I think it was in year 10, in fact, but you'd have revisited it somewhat. But plants get this from nitrates in the soil, therefore. But as you harvest plants, and you therefore have used the nitrate source within that particular patch of land, then obviously that soil will then be stripped of the essential nitrogen that is needed, and it doesn't get directly returned to the soil when you harvest that plant. So you have to have a way of therefore replenishing it and turning the soil or return it to its fertile state so that it helps further crops to grow. Okay, so ammonia is then used to make nitrate fertilizers to replenish this within the soil system itself. Okay, fertilizers, as again you've studied in biology, have both positives and negatives, but I will cover them in a few slides time because it's actually quite important for chemistry in particular to consider whether they are a good thing or a bad thing. But let's go back to deciding something I touched on earlier. What conditions would you choose if you were performing this Haber process? Okay, so what are the conditions? Okay, I would say that if it's something like a QER, so an extended answer that they're looking for, you'd need to have the building blocks of what are the conditions as the base. So what are they? Do you know them? Can you recall them? And then if you're aiming for the higher tiers, then you'd have to build upon not only recalling what the conditions are, but being able to explain them in quite a lot of depth if possible. So the conditions, and I will go through each of them and the rationale behind them as we go through them. So there is a catalyst present. Now, catalyst, if you remember back to year 10 rates, so unit 5 again, catalyst is something that speeds up a chemical reaction. Now be careful, because this reaction is reversible, as that symbol signifies to you there, don't be fooled to think that it makes, or the presence of a catalyst will make more ammonia, okay? Because not only does it catalyze the forward direction that's making the ammonia, it also catalyzes and makes this reverse reaction also faster. So it doesn't make any more product, it simply makes that product in a smaller time frame. Okay, so you are expected to recall that there is an ion catalyst present. You are also expected to recall near enough the exact temperature. So it's in the range between probably about 350 and 450 degrees C. Now, in general, industries are now leading towards the higher end of that range, so about 450 degrees C. Admittedly, sitting in a room that would be 450 degrees would be uncomfortable to say the least, but in chemical terms, that is not described as a particular high temperature, but neither is it a low temperature. It's what they've described as an intermediate, so it's in the middle. It's a middling, medium type of temperature, okay? It has a high pressure, okay? Now, atmospheric pressure, this unit here, describes exactly that. So the natural pressure presence would be classified as 1 atmosphere. Doesn't want to write for me for some weird reason. So if naturally 1 atmosphere is what's present, the fact you then have it 200 times more pressurized means there must be a reason for doing this, and I'll go through it in a minute. Okay, so let's go straight for that. Why high pressurized then? Well, as I said earlier, we have got 1 and we have 3. Okay, and it is making a total of 2 things. So if you have 4 making 2, any increase in pressure, so high pressure in this case, will force the equilibrium to go forward, because that's the natural method for decreasing that internal pressure within the system. Okay, so high pressure pushes the equilibrium to the right-hand side, making more product, because that's what's on the right-hand side, and it increases what we describe as the yield, so how much ammonia you actually get. Okay, so this is always going to be the case though. So the equilibrium will always move to the side with the fewer molecules. So you need to be looking at, okay, the numbers within the balance, and that is the key thing as well. Make sure that you've balanced the equation in the first place. So once it's balanced, which side has the greatest number of molecules and which one has the least? Because the high pressure will force it to the side with the smallest or fewer number of molecules. Okay, so 200 atmospheres. If it's that good a thing, surely we should be doing it at 400 atmospheres or 500 atmospheres. Okay, well, they only go as high as 200, and there's a reason for that. And the reason is achieving a very high pressure, so even higher again, would be even more expensive. Okay, on top of that, as you increase the internal pressure of any system, then it also brings with it a sense of health and safety. So to contain that system, the equipment used would need to be very, very strong. Okay, so what they do is they decide like 200 atmospheres is a good compromise, and this is a word that they do love when you're writing about Equilibria, compromise, because there's always a compromise to be made. So 200 atmospheres is a good compromise. So you still get a pretty high yield, okay, but you minimize the factory costs, so it becomes more economical. And it's also safer, of course, because you don't have this need for extremely strong equipment that, let's be honest, if things go wrong, could potentially explode and cause quite a lot of damage. So compromise 200 atmospheres is what they go for. So recall the pressure, 200 atmospheres, be able to explain it confidently. Great, okay. Right, how about temperature then? Because as we described earlier, when you're looking at temperature, you need to be looking at whether the reaction going forward, so the one in the right-hand side direction, is it an exothermic reaction or is it an endothermic? So is that reaction naturally going forward going to give out heat, or is it going to take it in? Okay. Well, in the Haber process, if you think back to unit 2 again, or session 2, sorry, that I did a few weeks ago, you would have been introduced to that symbol delta H, so enthalpy, and in this case, it is a negative number. Now, a negative delta H is indicative or tells you that the reaction is exothermic, okay? So the key thing to get your head around here is that you do indeed have the forward reaction being exothermic, but that means that going backwards and remaking the reagents nitrogen and hydrogen would be an endothermic reaction. Okay, so that is a method, if need be, that the system could absorb the energy you might be inflicting or imposing on it. Okay, so a low temperature, that is the one that will then favour the right-hand side. So if you reduce the temperature as much as you possibly can, it'll mean that it'll go forward a bit more than it did initially. Okay, so it increases the yield of ammonia. Great, that must mean I should do this at really, really cold temperatures, wouldn't it? Or would you? Okay, so we're coming to that in a minute. So at a low temperature, the rate of reactions, however, is too slow. So we're linking back again to something you did in year 10, which is the rates unit. In that, you were told, and that stands and still is true, that a high temperature makes a reaction faster. So despite the fact that going back to this point, which is that a low temperature favours how much ammonia you get, so favours the forward direction, a low temperature kind of unmakes that or undoes that good by the fact that, yes, you're making more ammonia, so you end up with more of this stuff, but you're ending up making it in a much, much larger time scale. So you're making more stuff, but it's taking a lot longer. Okay, and that's because of the particles, if you reduce the temperature, colliding a lot less, so the less of them are achieving that crucial activation energy. Okay, and don't forget, in industry, time is money. Okay, so if you can make things in a faster time, you can sell it in a faster time. So that bit, which is called rates, tells you let's do it at a really high temperature, because high temperature makes it really fast. I can make the stuff faster. Okay, so high temperature would push the equilibrium to the left. Okay, because it's the side that will absorb it, but a low temperature pushes it to the right, but makes it really, really slow. So what do you go for? Well, as I discussed earlier, you go for a halfway house. So you go for a compromise again. Again, they do love that word compromise. So they use this temperature of 450 again, because it is a compromise. It is the compromise between getting as much as you possibly can, which is therefore pushing it as far to the right as you can, but also making sure that the rate of the reaction is still reasonable. It's pointless getting more ammonia if it takes twice as long to make it. So they go for this compromise, and they've done this. They've tried and tested the most convenient and economical, because as I said, industry, time is money. You basically need to find the right balance between getting as much as you can so you can sell as much as you can, but getting it in a time frame that still makes it economical for that company. Right, catalyst is the third condition you need to know about, but be clear, as I said earlier, an ion catalyst increases the rate of reaction, but it has no effect on how much you make. Okay, so it's not the fact that it makes more ammonia, because it not only catalyzes the forward reaction, but it also catalyzes the backward reaction at the same or to the same extent. It simply means that you're getting to that equilibrium in a faster time or a shorter time frame. So be clear, conditions are you need to have it at a temperature of about 450 degrees C, you need a pressure of around 200 atmospheres, and you need the presence of an ion catalyst. Now, I did mention it in that section, but also it might be worth mentioning the fact that the ion catalyzing it is usually present as a bed or a flat block of iron. And that is again linked back to that unit 5 in year 10, which is the fact if you've got a larger surface area, then it simply means that you can get that reaction being or taking place in a shorter time frame again. So it's increasing surface area. So you have beds of iron catalysts, okay? Right. There's always going to be a mixture of nitrogen, hydrogen, and ammonia within the system. So another way or another trick that industry have come up with of making it kind of faster is by removing this. So if you can take the ammonia being made and take it away, the system will kind of go, it's not as simple and straightforward as this, so they haven't got emotions and stuff, but they kind of say, oh my God, they've taken away my ammonia, I'm just going to make more of it. Because that's all about, it's all about trying to get back to the status quo of what it was. So if you are hot, it's about trying to cool yourself down. If you're pressurized, it's about trying to reduce the pressure. In this case, if you're trying to make ammonia and you remove it, it'll try and make more. So it's always about trying to get back to the status quo, okay? So how do we get ammonia to be pure? Well, ammonia has a higher boiling point than hydrogen and nitrogen, so you can separate it by condensation again. Okay, so easily separated, and as it's cooled, okay, the ammonia condenses and that can then be removed as a liquid product. Right, so you collect the liquefied ammonia. Anything that wasn't used up, so any hydrogen and nitrogen that remained, it simply gets pumped back into the beginning. Okay, so the hydrogen and ammonia are recycled back into the reaction vessel, and the whole process starts again. So they don't have any wastage. Anything that is wasted or not reacted, they pump back to try and make it react again. Okay, so I touched upon it earlier. Fertilizers. Now, ammonia is a colorless gas. It's highly soluble in water. It has that potent, quite choking smell to it. Ammonia is also alkaline, so will perform, if you think back to the acids and bases unit, it will perform neutralization reactions because of this alkaline nature. Okay, it's also worthwhile recalling and pointing out here that ammonia will then turn damp red litmus paper blue. Okay, so actually the test for ammonia gas is that it turns damp red litmus blue. Okay. And it's all down to the fact that ammonia is a weak alkali. Okay, so ammonium compounds, if you think back to the units, I'm not going to dwell too much on it, for the reactions of neutralization, ammonia will quite happily form ammonium salts. Okay, so if you remember correctly, metal, alkali, base, or carbonate, all of them will produce salts. Now, ammonia will simply produce ammonium salts, so NH4 plus salts. Okay, so you've got ammonium chloride, ammonium sulfate, ammonium nitrate. Now this one's probably the most expensive fertilizer, and that's because it's got 2 sources of nitrogen, which makes it like a double whammy for farmers. Okay, so ammonium ion, as I said, ammonia will turn damp red litmus paper blue, but if you want to produce the ammonia in itself from an ammonium salt, you simply have to add a bit of sodium hydroxide to it. Okay. Right, so as I said earlier, and this has been covered in biology, the whole point of fertilizers is to improve the quality of the plant growth. Okay, so we've got nitrogen, phosphorus, and potassium. All of them are quite important for plants, but we're going to focus just on the nitrogen one and the fact that plants can't get them out of there. So I'm not going to dwell too much. But there is a downside, okay, for fertilizers. So just quickly, I'll come back to the end possibly, okay. So ammonia, sulfuric acid, and nitric acid are all compounds that are classically used in making fertilizers, okay. Right, the second process, and this is slightly easier to understand if you've been listening to the rationale about the Haber process. Contact is a method for making this, which is something you've always been familiar with. Hopefully now you'll recognize the formula. It's the process for making sulfuric acid. Now again, sulfur goes in. This is slightly more complex in the sense that there are 3 equations to recall, but only one of them is reversible. So from beginning to end, you pump in air, you burn sulfur in it, and it makes sulfur dioxide. And then that sulfur dioxide is further reacted to make sulfur trioxide, and that sulfur trioxide then dissolves into water to make sulfuric acid. So there are 3 stages, and I'm sorry to tell you, you're going to have to learn all 3. The only one that really plays a part in what I've been discussing today is that second one, because it's the only one with this reversible symbol. Okay. Again, let's focus on what conditions, therefore, you would think would be optimum or ideal for this. Okay. So we've got 3 molecules going to 2. Okay. That means that there is some reduction in pressure by going forward, but it's not enough or a significant amount of decrease in pressure to justify a hugely high pressure. Okay. So the conditions used for this, again, that intermediate compromised temperature of about 450. So they don't go for too high because that would reduce the yield, but they don't go for too low because that would mean that it's too slow. Okay. Atmospheric pressure. Again, you'd think that just above it is what they actually is, just above atmospheric, and that's because the 3 to 2 isn't significant enough to make it worth the cost of pressurizing the system as a whole. And as was the case for Haber, you're going to have a catalyst, and in this case, the catalyst is this compound here. It's called vanadium 5 oxide. I would simply learn the formula, or if you're more comfortable learning the name, then vanadium 5 oxide, but be careful, okay? It should be a V in there, especially for higher tier pupils, or vanadium oxide, okay? Now, be clear why the temperature and the pressure are as they are. Admittedly, initially you'd think possibly that atmospheric pressure would be unideal, but it's simply because pressurizing it is costly and it doesn't pay back. Industry, time is money, and if you can save money, then that's what industry does. So remember the conditions, as was the case for Haber, and be able to explain them with a bit of confidence why those conditions are used and chosen. So what do we have as the uses for sulfuric acid? Well, you have to be able to recall at least a few of these. So maybe not all 7 that I've listed there, but if you can have a few standard ones in your head, then that's a great thing in itself. Okay, so it's the acid in car batteries most of the time. Okay, it's used for making detergents. It's a dehydrating agent. Apologies, I've forgotten to move the picture over, but it should say dehydrating agent. I'll correct it before it goes on the site. Okay, so learn a few. So have a few standard uses of sulfuric acid. Okay, right. To finish off, admittedly there is a few past papers at the end, but that is for you to just self-assess after this session, so it's not to be done this evening, but there are a few past paper questions I'll touch upon in a second or two. But let's be clear, what is the good side and what are the bad sides of fertilizers? Now, most sulfuric acid that is produced is actually directly used to make fertilizers. So out of all of those uses that we had there, the major one, okay, that is made from sulfuric acid is actually the manufacture of fertilizers. Okay, so be able to recall a few of these. So classically, if you combine ammonia with sulfuric acid, it'll make the salt ammonium sulfate. Okay, so be able to give, at the very bare minimum, a word equation, but ideally push the boat out and try getting a symbol equation as well. Okay. Now, why are they so useful? Well, it's all to do with the fact that they are nitrogen-rich compounds. Okay, and if you can replenish that nitrogen within the soil, you can make it get fertile again, and plants can regrow successfully for another kind of cycle or another crop. Okay, pros and cons though. Okay, they aren't all lovely and ideal. There are downsides to fertilizers as well, but let's go through the positives first. Okay, so they increase crop yields. There's no doubt that is a good thing. You can make more food if it's a food crop, or you can make more plants. Okay, they tend to make healthier plants as well because you are replenishing them and supplying them with sufficient amount of nitrogen. They're relatively cheap. Okay, and it does in some cases turn unfertile soil or poor quality land into much better quality land can then be used for cultivation of crops. Okay. Downside though, and this is a word you came across in biology, I would strongly advise you don't try describing it in chemistry. You will get the credit simply for saying the word eutrophication. In fact, you're often penalised for trying to describe it, because if you're going to go and push the boat out and describe all the stages for eutrophication, as unfair as it might sound, it does mean that you don't get credit. If you miss out a single stage, you don't get credit, but you will get credit for simply using that one word, eutrophication. Okay. And the other downside, which should be briefly mentioned, is a condition called blue baby syndrome, which unfortunately often proves fatal to newborn babies. And it's all due to the fact that if fertilizers get into waterways and the water supply, it can stop successful oxygen transportation within the womb. Okay, so when that baby is born, it is born with a blue coloration due to the lack of oxygen. It's called blue baby syndrome and is often fatal. Okay, so as I said, there are a series of past paper questions. What I suggest you do is that you download the PowerPoint after this evening and you literally go through them at your own pace. There is a mark scheme after each question, you'll be pleased to know. So after each one, you'll see the mark scheme. So try the question, look at the mark scheme. Try the next question, look at the mark scheme. Okay, so I'm hoping that you found that useful. And this is the last session, so hopefully you found all the sessions useful. But regardless of whether you are doing double or triple, good luck in your exams in what will be a scary amount of weeks. Good luck to you all.